So in this problem, we have a ball bearing, an iron ball bearing that's 8 inches in diameter, and it's coated with a layer of ice, however thick. Okay. Now, it says if the ice is melting away at a rate of 10 inches cubed per minute, then how fast is the thickness of the ice decreasing when it is 2 inches thick? Okay, so here's the ball bearing, let's say, and we're told that the diameter here is 8 inches, and then there's like a layer of ice around this, right? And the volume of this whole sphere is 4/3 pi r cubed. Okay, and we want to know when the ice is 2 inches thick, what is it wants to know how fast is the thickness of the ice decreasing. So really, we have this distance, and we want to know how fast this radius is moving in at that point. Okay, so when the ice is we want to know dr dt. Okay, and we're told at that point the volume here is dv dt is 10 inches cubed per minute. Okay, so now I'm going to write the formula here. I don't think there's any substitutions or anything that we have to do. We can just take the derivative of both sides with respect to t. So dv dt is equal to, now this is going to be, bring the 3 down, 4 pi r squared, but then I need a dr dt. That's the implicit differentiation. And then I can do dr dt is equal to dv dt all over this here, 4 pi r squared. Okay, now let's think about it. What is r when the ice is 2 inches thick? So this and this is 2 inches thick. Well, the diameter of the sphere is 8 inches, so the radius at this point of just the sphere is 4 inches. So you have the 4 inches and 2 more inches. So it looks like we want to find dr dt when r is equal to 6. Okay, and so the dv dt is that 10 inches cubed per minute divided by 4 pi, and this is going to be 6 squared, like that. Okay, so this would be, I guess I could cancel out 5, and then I'd have like a 2 pi times 36, and that'd be like 5 over 72 pi. And then I guess I could get an approximation here. 5 divided by 72 times pi. And so it's approximately 0.0221 inches per minute. Okay, so yeah, it's pretty slowly. It's ice melting away, and that's what it is, that many inches per minute. Okay, that's the exact answer. So there's a second part to this problem, and it is, what is the rate of decrease in the surface area of that ice? And the surface area, we'll say the area, surface area, let's just say SA. The surface area of a sphere is just 4 pi r squared. And here's an interesting thing, is that when you take the derivative of the volume, you actually get 4 pi r squared. So the rate of change of a volume at a certain instant is the surface area. So as the r is decreasing, as it goes in, what it loses is that outer layer, that, and so the surface area is actually the derivative of the volume. It's kind of an interesting thing here. Well, taking that formula, see if you can find the rate of change of the surface area of this sphere at that same time when the ice is 2 inches thick. So go ahead, give it a try, press pause, give it a try, and then you can start the video back up again. Okay, so let's see how you did here. I'm going to take this formula, and I'm going to take the derivative of both sides with respect to t. So I'm going to get this, and then when I take the derivative of this, I get 8 pi r dr dt. Okay, and so now I'm going to, well, this is what I want to find, the rate of change of this surface area, right? So I don't have to solve anything here, right? But I do need to know the rate of change of the radius at that time, which I actually have right here. I actually found it right here. So to actually find this ds dt, when we can say when r is 6, is just going to be 8 pi times 6, and then all of this multiplied by this, 5 over 72 pi. Okay, so when you do this, you actually, you can reduce here, the pi's cancel out, 72, this would cancel and give you a 9, and this would cancel and give you, or that just cancel out completely. The 6 here would cancel out and give you 2, and this would cancel out and give you 3, and so it looks like I would get 10 thirds inches squared per minute. So this is actually what you would get for the rate of change of the surface area. Okay, so there you go. Another related rates problem here, and I think maybe I'll do another one here. We'll do at least one more here.